Imagine a machine so powerful it can heat substances to 200 million degrees Celsius. Japan's JT60SA is exactly that. This fusion reactor boasts an advanced magnet system with 18 massive coils and a central solenoid, all supercooled with liquid helium to endure extreme conditions. But what if something goes terribly wrong, leading to a catastrophic scenario? Could the consequences of tampering with such formidable forces be beyond our control? Join us as we uncover the potentially dangerous outcomes of harnessing this intense force. JT60SA's Fusion Frontier. The JT60SA uses the latest plasma control technologies to make sure everything runs smoothly. It has advanced systems for heating and driving current, which help keep the plasma in the right conditions. These systems work with various control tools, like magnetic coils and extra heating mechanisms, to make fine adjustments to the plasma's shape and stability. This precise control is key to preventing problems and making sure the plasma stays intact, which is crucial for generating fusion energy. However, that's not the end of the story. Another exciting feature of the JT60SA is its ability to support long-term research. This tokamak is not just about solving today's problems, but also paving the way for future innovations in fusion technology. The JT60SA project is leading the way in a global effort to use fusion energy, the same power that fuels the sun. Located in Japan, this facility is more than just a reactor. It's a testing ground for the future of energy. Its main goal is to experiment with different ways to control plasma, the hot, charged gas needed for fusion. By doing this, JT60SA aims to make reactors more efficient and reliable, which is crucial for powering our world. The experiments here are important because they help scientists understand how to keep plasma stable inside a reactor, a key part of making fusion energy work. But there's more to this story. The JT60SA project is crucial because it doesn't just advance its own research, it contributes significantly to international efforts in fusion energy. The breakthroughs here are shared with the ITER project, helping to solve challenges and improve processes. This collaboration accelerates the progress of fusion science and gets us closer to harnessing fusion power for everyday use. By perfecting these technologies, JT60SA is laying the foundation for a future with cleaner, sustainable energy sources. The JT60SA project is making big changes in the world of nuclear fusion, always updating its research to keep up with new discoveries at ITER. At first, it was supposed to help ITER, but now JT60SA is focusing more on what future fusion reactors will need. The project's goals are growing to include better steady-state operations and exploring new plasma scenarios, which are the conditions we expect in future fusion power plants like DEMO. It's also about working together internationally, especially between Europe and Japan. This cooperation is crucial, not only to tackle the technical and logistical challenges of such a complex project, but also to build a strong team of skilled researchers and engineers. This growing community is key to keeping and expanding the knowledge needed for future fusion projects. Let's see how JT60SA is pushing us toward a better future. #JT60SA's path towards endless energy. JT60SA is more than just a research facility. It symbolizes future energy possibilities. It uses the latest superconducting magnet technology and advanced plasma control systems, setting a high standard for future projects. The facility shows the potential of fusion energy to become a sustainable, endless power source. But this isn't the end of the story. As JT60SA progresses, it will greatly improve our understanding of plasma physics and help make fusion energy a practical reality. This marks a critical step toward a groundbreaking power solution that could forever change how we generate energy. Japan's cutting-edge fusion reactor, JT60SA, uses a set of powerful magnets to hold a superhot gas called plasma in a donut-shaped chamber. This impressive piece of technology, the largest and most advanced reactor in the world, is crucial for the International Thermonuclear Experimental Reactor, ITER, project in France. It helps scientists understand the complex science of fusion energy. On October 26, 2023, after almost 15 years of careful development and testing, JT60SAA reached a major milestone by creating its first plasma. This big achievement shows the world that the reactor is working as planned. Sam Davis, the project manager at Fusion for Energy, excitedly confirmed that everything is functioning perfectly. Fusion for Energy, a European Union organization, works closely with Japan's National Institutes for Quantum Science and Technology to track and study the reactor's progress. The core process in the JT60SAA reactor is nuclear fusion. This is when two smaller atomic nuclei join together to make a bigger one, releasing a huge amount of energy. This reaction happens in a special state of matter called plasma, which is extremely hot and full of charged particles. Successfully controlling this process is not just a big scientific win. It could also lead to nearly endless energy sources, just like the reactions that power the sun. But that's not the most challenging part. Even with the first plasma success, scientists face ongoing challenges in managing and maintaining such a powerful reaction. The work is far from over, but the progress so far is a big step forward. Plasma is a unique form of matter that's different from solids, liquids, and gases. It's made up of freely moving electrons and positive ions. This special mix is what powers the sun and all other stars. In the sun's core, atomic nuclei bump into each other at extremely high temperatures, around 10 million degrees Celsius. These high temperatures give the energy needed to overcome the electrical push between the nuclei, allowing them to fuse together. This fusion happens because, at close range, the attractive nuclear force is stronger than the repulsion. For fusion to occur, the nuclei need to be packed closely to increase the chances of these collisions. The sun naturally achieves this because of its intense pressure and gravity. But why are scientists so interested in fusion energy? The fascination with fusion began in 1925 when British scientist Arthur Eddington suggested that stars like our sun get their energy from nuclear fusion, combining hydrogen nuclei to form helium. Inspired by this natural process, scientists have been trying to harness this powerful reaction to produce vast amounts of energy. Since the 1950s, the idea of fusion has captivated many because a fusion power plant would generate significantly less radioactive waste compared to traditional nuclear reactors that rely on fission, the splitting of uranium atoms. But this isn't the biggest challenge. Now, dive deeper into the science that could make fusion a reality. #, the pursuit of practical fusion energy. A single gram of hydrogen isotopes, which are used as fuel for fusion reactions, could produce as much energy as almost 10 metric tons of coal. Since scientists first understood the theory of nuclear fusion, they have been working hard to replicate and use this process. Nuclear fusion, if harnessed effectively, promises to provide a nearly limitless supply of safe, economical, and clean energy, potentially meeting global energy demands. However, the difficulty of replicating fusion on an industrial scale remains a significant hurdle. Trying to achieve fusion energy on Earth is tough, but could be revolutionary. Fusion energy can produce 4 times more energy per kilogram than the nuclear fission used in current nuclear power plants. This stark comparison drives scientists worldwide to relentlessly pursue turning the concept of fusion into a practical energy solution. And yet, the journey is far from over. Imagine a power source that's about 4 million times stronger than burning fossil fuels like coal or oil. Most fusion reactors being developed today use a mix of tritium and deuterium, which are types of hydrogen atoms with extra neutrons. In theory, just a few grams of these materials could produce enough energy to power a developed nation for 6 years. This fusion fuel isn't just powerful, it's also quite accessible. Tritium can be made by fusion-generated neutrons interacting with lithium, which is naturally found on Earth. Deuterium can be easily taken from seawater. We wouldn't run out of these resources for millions of years. Plus, unlike traditional nuclear power, fusion doesn't create long-lasting radioactive waste that can harm the environment and our health. But this isn't the most impressive part. Future fusion reactors are being designed to be very safe. They operate under such controlled conditions that if something goes wrong, the fusion reaction would just stop. The plasma needed for the reaction would naturally dissipate. This safety feature means fusion power could be a huge step forward in our search for clean, sustainable, and safe energy solutions. Nuclear fusion uses up its energy very quickly, which stops it from causing any long-lasting damage to the reactor. This fast energy use makes sure there's no risk of an uncontrollable reaction or a major meltdown. Unlike other nuclear reactions, starting and keeping fusion going is very hard. However, both nuclear fusion and fission are good for the environment because they don't release greenhouse gases. As we look to the future, nuclear fusion could become a reliable source of low-carbon electricity. The sun's strong gravity makes fusion happen naturally, but doing this on Earth is much harder. To start fusion with deuterium and tritium, the materials used in this process, temperatures must go over 100 million degrees Celsius. It's not just about high temperatures, though. Controlling magnetic forces and maintaining the right pressure are also very important. These elements need to be managed carefully to keep the plasma stable and the fusion reaction going long enough to make more energy than it took to start it. Current experiments are getting close to the needed conditions for a fusion reactor. However, there are still big challenges like better energy confinement and plasma stability that need to be solved to make nuclear fusion practical. But this isn't the hardest part. Achieving and maintaining these extreme conditions is very tricky and expensive. Scientists are working hard to find solutions, but it will take time and more research. Still, the potential benefits of nuclear fusion are huge, offering a nearly limitless and clean energy source for the future. Next, explore how teamwork worldwide is making fusion possible. The global quest for fusion energy. To achieve net fusion energy, scientists and engineers from around the world are working hard, trying new materials and creating advanced systems. Over 50 countries are involved in nuclear fusion and plasma physics research, making significant progress. Recently, scientists achieved a net energy gain from a fusion experiment for the first time. This breakthrough came from new designs of magnet-based fusion devices like tokamaks and stellarators, as well as innovations using advanced fuels, lasers, and other techniques. The key to successfully harnessing fusion energy lies in how quickly the industry can advance and approve new fusion technologies. It also depends on the ability to gather enough resources through global partnerships and cooperation. Developing a strong nuclear infrastructure, including standards and best practices, is also essential for this new energy source. One of the major fusion projects is the JT60SA in Japan. This reactor is designed to heat plasma to 200 million degrees Celsius and keep it at that temperature for about 100 seconds. This allows researchers to study and improve plasma performance and stability, which are crucial for efficient fusion power. The JT60SA supports ITER, a huge international fusion reactor being built in France. ITER aims to show that fusion energy can produce more power than it uses, relying on the expertise and innovations tested by JT60SA. Japan was also given permission to build JT60SA and 2 other smaller fusion facilities. This was in exchange for France hosting ITER, the largest fusion experiment ever. This agreement was part of a larger 2017 deal between the EU and Japan, which also included updating Japan's older JT6 reactor, in use since the 1980s. This global effort shows a shared commitment to revolutionizing energy production through fusion, setting the stage for a big change in how we generate power in the future. This cooperation marks a significant step towards cleaner and more efficient energy solutions. The world is watching closely as these projects develop, hoping for a future where fusion energy becomes a reality. This collaborative spirit among countries highlights the importance of working together to tackle global challenges and find innovative solutions. In the mid-1980s, the complete rebuild of the reactor started from scratch and was kept very secret. Called JT60SA, which means Super Advanced One, this reactor is much smaller than ITER, being only about half its height. Even though it's smaller, it can hold a lot, up to 135 cubic meters of plasma, which is about 1/6 of what IEA can hold. Alberto L., who leads the science division at ITER, said the data from the JT60SA plasmas would be very useful for improvements at ITER. However, rebuilding this reactor took much longer than planned. It was supposed to be ready in 2016, but many unexpected problems pushed the finish date to over 15 years later, according to Science.org. The team faced many challenges, including big issues with getting supplies. This forced them to redesign the reactor to make it strong enough to handle the March 2011 Tohoku earthquake. Then, in March 2021, during some tests, another major problem popped up. A short circuit happened in the cable connected to one of the superconducting magnetic coils. This not only messed up the electrical connections but also caused a helium leak, adding more trouble for the development team. During a crucial moment, a leak almost caused serious problems for the cooling systems. This happened when the circuit's electricity flow was at its lowest. According to the QSD project manager, Hoshirai, the situation was very serious. He explained that the coil could have been badly damaged if the electricity flow had been higher during the incident. The JT60S team was relieved, recognizing how lucky they were that things didn't get worse. From big wins to big challenges, fusion's journey is far from over. Japan's bold leap toward sustainable energy. After this close call, the team spent 2.5 years fixing the insulation on over 100 electrical connections to make things safer. This accident made ITA developers decide to do more thorough testing on their coils to avoid future problems. However, there's still a major issue with the JT60SAA. It only uses hydrogen and its isotope deuterium instead of tritium. This choice limits its broader use and effectiveness in certain reactions. This shows the tough decisions and trade-offs involved in developing such complex technologies. Tritium is a special type of hydrogen. It's stronger, more expensive, rarer, and more radioactive than regular hydrogen. It's very important for making electricity through fusion, a new technology that could change how we power our world. The International Thermonuclear Experimental Reactor, or ITER, plans to use tritium by 2035 to create this new energy. Japan aims to become a leader in fusion energy, with a big goal of having a working fusion power plant, called DEMO, by 2050. This plant is supposed to move from experimental projects like JT60SA and ITER to real, commercial fusion power generation. The main aim of DEMO is to show that it's possible to consistently produce net electricity from fusion, which would be a huge step towards sustainable energy. DEMO aims to be one of the first plants of its kind in the world. It's working on solving major problems like keeping stable fusion plasma going for long periods and managing the fuel cycle, especially dealing with tritium, a key part of fusion fuel. These are big challenges but crucial for showing that fusion energy can work on a large scale. At the center of Japan's fusion efforts is the JT60SA reactor, which is smaller but similar to ITER. This reactor is important for developing the technologies needed for DEMO. Even though it has faced delays due to natural disasters and technical problems, JT60SA is still a key part of Japan's fusion research. But that's not the worst part. Japan is also looking beyond just experimental reactors. The government has started the Fusion Energy Innovation Strategy to boost Japan's role in international projects like ITER and to build the industrial skills needed to create and maybe export commercial fusion reactors in the future. Japan's strategy includes making strong international connections, especially with European partners through agreements like the Broader Approach. This helps in sharing technology and knowledge and in training new fusion specialists. Developing these experts and the necessary materials and technologies is crucial for future reactors. With these plans, Japan is putting a lot of effort into both scientific research and industrial development needed to lead the next generation of energy technology. This bold plan shows Japan's commitment to taking a top spot in the future energy world and its dedication to overcoming the big technological challenges to make fusion a groundbreaking energy source. But here's the exciting part. A key player in fusion energy, SHI, is thrilled about these developments. Recently, a lot of new ideas and money have come into fusion energy because private companies are investing. SHI thinks it's great that more people are getting involved. This interest shows that many see fusion energy's potential to change how we generate power, making it cleaner and more sustainable for everyone. What are the potential downsides of fusion energy? Share your views. If you enjoyed this video, don't forget to like, leave your thoughts in the comments, and subscribe for more.